Good day, everyone. We are reviewing Wetzel's Limnology textbook. This is edition number 4, and we are focusing on chapter 11, which deals with oxygen and oxygen distribution in lakes and rivers. And more specifically today, we'll be looking at oxygen distribution in lakes. And so let's get started. This is subsection A, orthograde oxygen profile. For lakes that are very oligotrophic, primary production and respiration can be so low that oxygen concentrations are regulated largely by physical processes. Throughout the year, the lake exhibits approximately 100% saturation at each depth, regardless of whether it is mixed or thermally stratified. Due to the colder waters in the hypolimnion, oxygen concentration actually increase in the deep waters. During stratification, this oxygen profile has been termed orthograde because most lakes have at least some biological activity. Orthograde conditions are rare and found only consistently in a few extremely unproductive lakes or in moderately oligotrophic lakes during the early stages of summer stratification. Because of increased primary productivity in many water bodies due to climate and land use change, the number of lakes exhibiting orthograde profiles may be decreasing. So let's look at figure 11-13 here. So time, depth, dissolved oxygen, left column, and temperature, right column. Observation from January to December illustrate A and B orthograde dynamics in Lake Waldo, C and D clinograde dynamics in Lake Erken, and E and F metalimnitic oxygen maximum, positive heterograde dynamics in Lake Stechlin, and G and H metalimnitic oxygen minimum, negative heterograde dynamics in Falling Creek Reservoir. The oxygen and temperature scales are the same for all 4 dimectic lakes. For comparison, white bars on the surface of lakes represent the ice-covered period, oxygen and temperature data from Lake Waldo, etc. Okay. So we have orthograde here, lake. So where we have even distribution of dissolved oxygen in the lake, pretty close to it. I mean, there's not really a change with depth and time. So y-axis is the depth, and then the color represents the concentration or the dissolved oxygen concentration in milligrams per liter. And then the x-axis represents a year, January through December. And then on the right side, it's the same lake, so it's a pair of lakes. I mean, it's the same lake, but a pair of data, I should say. And then this is temperature in Lake Waldo. So also, we are not seeing a lot of thermocline here. We are not seeing even like any change in stratification or any turnover whatsoever. So, and except for maybe it gets a little warmer at the surface, but it's definitely not it's not propagating to at depth. So there might be a little thermocline like starting maybe like June or mid-May to like November, early mid-November, and the depth is maybe at max probably about 20 meters. Cleaner grade dissolved oxygen. So this is for Lake Erken. So here we do see a change in concentration for dissolved oxygen, especially at depth for these lakes, and more than once. So here in this zone, especially in the summer. So in summer we have like a loss of oxygen at depth. And then the temperature there, we have a very, like this is a lake that shows thermocline, and I mean we have very stable temperatures, of course, in the winter and mid spring, and then as well as in the late fall. And then once again here, this is the ice layer, and so like for example this lake is getting frozen over until early April, where Lake Waldo is all the way to early May. This is an heterograde lake, so this is the opposite of an orthograde lake, where we are seeing variability in the dissolved oxygen concentration, both at depth and through seasons. And then the temperature is the temperature of that lake, and we can see that it's pretty well isolated. So there's a strong thermocline, and then the hypolimnion is pretty well stable in terms of temperature through time. And then this is a negative, so this is positive heterograde, and this is negative heterograde with Falling Creek Reservoir. And we'll look into the text as to what negative and positive heterograde mean. We haven't viewed that yet. Okay. So due to their very low biological activity differences in oxygen concentration and orthograde depth profile are driven primarily by the varying solubility of oxygen at different temperatures. As summer thermal stratification sets up, the oxygen concentration in the circulating epilimnion decreases as its temperature increases and solubility decreases, promoting evasion of the excess oxygen to the atmosphere. In contrast, the hypolimnion remained at the same oxygen concentration as it exhibited during spring turnover. As a result, oxygen concentration in the hypolimnion are higher than in the epilimnion during summer stratification, though the depth profiles remain at 100% saturated at all depths. In winter, due to inverse stratification, a lake with orthograde profiles will exhibit its highest oxygen concentration just below the ice. Orthograde profiles exhibit minimal to no oxygen depletion at the sediment during stratification. Data from Lake Waldo generally support the conceptual model of a lake exhibiting orthograde dynamics presented in Figure 11.12. Lake Waldo is a glacially formed alpine lake with summer Secchi depth greater than 30 meters. The lake has a small watershed without any tributaries contributing to its low productivity. In the summer, hypolimnetic oxygen depletion is not observed, and the oxygen profile is marked by relatively low variability throughout the year. Unlike the conceptual model, however, Lake Waldo exhibits hypolimnetic supersaturation in the summer. Its high transparency enables solar radiation to reach deep layers and slightly warms the hypolimnion, decreasing oxygen solubility. Since the excess oxygen in the hypolimnion cannot be vented to the atmosphere, oxygen supersaturation occurs. Although plant and animal respiration can occasionally consume large amounts of dissolved oxygen, generally its contribution to total biological oxidation is much smaller than microbial decomposition of organic matter. Oxidation of reduced substances released into the hypolimnion from the sediments can also contribute to clinograde dynamics. The relative importance of different mechanisms of hypolimnetic oxygen depletion varies among lakes. In lakes less than 100 meters, deep oxygen demand is typically dominated by the microbial decomposition of organic matter at the sediment-water interface. The flux of reduced substances can also contribute to hypolimnetic oxygen depletion in these water bodies, with hypolimnion depth inversely related to its importance. In very deep lakes, greater than 100 meters, the decomposition of autochthonous organic matter is mostly complete by the time it reaches the sediment. And thus, water column respiration of sedimenting organic matter dominates. Conversely, in highly stained bog lakes, photochemical oxidation may assume greater significance, resulting in undersaturation even in the epilimnion. Fall turnover results in oxygen-saturated water reaching the bottom layers before ice onset ceases the exchange of oxygen with the atmosphere. Without circulation, most eutrophic lakes will exhibit some depletion of oxygen during the ice-covered period at the sediment. Oxygen-consuming processes occur throughout the winter, although at a lower rate than in the summer because of the colder temperature. Photosynthetic production continues throughout the winter and is often high during the later stages of winter ice cover, matched in some lakes by high respiration. Light penetration is variable with changing conditions of ice and snow cover, but the photic zone is generally confined to the upper layers. The annual stages of a lake exhibiting clinograde dynamics, shown in figure 11-12, are for the most part exhibited by Lake Erson. But these data reveal overall much greater within-season variability. Noteworthy is the variability in oxygen under the ice from January to late March, likely due to the physical process followed by high oxygen during spring circulation in early April. Oxygen depletion at the sediment is evident despite mixing occurring in the upper portion of the water column from mid-April to the end of May. Depletion accelerates after the onset of thermal stratification in early June, resulting in anoxia throughout the apolimnion by late summer, which favors the accumulation of reduced substances. Summer variability in epilimnetic oxygen is likely due to phytoplankton, which is halted by fall turnover in mid-September. Uniform oxygen concentration throughout the depth profile at 100% saturation persists throughout the remainder of fall as the water temperature gets colder. Metalimnetic oxygen maxima. Two variations in the vertical distribution of dissolved oxygen from orthograde and clinograde conditions are often observed. The first is an increase in oxygen in the metalimnion during stratification, which is referred to as either metalimnetic oxygen maximum or a positive heterograde curve. As the solubility of the epilimnetic water decreases with increasing summer temperatures, thereby decreasing oxygen in the surface water, and hypolimnetic depletion decreases oxygen in the bottom waters, and oxygen maximum in the metalimnion can emerge relative to the rest of the profile. Metalimnetic oxygen maxima can sometimes be extremely pronounced, with supersaturated value recorded above 300% and even above 400%. The development of metalimnetic oxygen maxima can be attributed to both physical and biological processes. The dominant physical process is the trapping of a layer of cold water with high oxygen concentration under the thermocline as thermal stratification sets up after spring mixing. Solar radiation warms this layer, decreasing its oxygen solubility and thereby increasing its percent saturation above. This oxic layer can persist until mixing occurs or the oxygen is depleted by biological and chemical oxidation. Interflow of oxic water from inflowing streams into the metalimnion may also contribute to the formation of an oxygen maximum. Biological processes can also form metalimnetic oxygen maxima. Deep chlorophyll maxima are widely observed in many lakes, driven by subsurface aggregation of multiple phytoplankton taxa. In some lakes, it is estimated that up to 60% of aerial primary production is attributable to deep chlorophyll maxima. The phytoplankton optimize their vertical distribution to ensure sufficient temperature and light for growth, as well as access for higher nutrient at depth, which are ideal conditions for mixotrophs. High density of submerged macrophytes are also associated with metalimnetic oxygen maxima. The relative contribution of physical versus biological processes in driving metalimnetic oxygen maxima is debated. Wilkinson observed that physical processes dominated by the formation of metalimnetic oxygen maxima in 17 small temperate lakes. In contrast, Moore et al. Found that physical processes were less important than biological processes in driving Lake Michigan's chlorophyll maxima. If a metalimnetic layer is extremely supersaturated, it is likely that biological processes dominate because only primary production can increase oxygen saturation much above 100%. Data from Lake Stechlin in Germany illustrate a persistent metalimnetic oxygen maxima throughout summer stratification. Both physical and biological processes likely contributed to its development. First, the maximum developed as stratification is set up in May, trapping cold oxic water below the thermocline. Solar radiation warmed this layer, decreasing its solubility and gradually increasing its percent saturation to 123% by late August. Second, the lake has a deep chlorophyll maximum of phytoplankton that repeatedly sets up at 10 meters, coinciding with the oxygen maximum. So let's look at figure 11-14 here. So these are depth profile of dissolved oxygen concentration during the summer in hypereutrophic Lake Johnson in New Zealand. In November, the lake exhibited a metalimnetic, so let's look at that before that. So the y-axis, we have the depth, and on the x-axis, we have the month. And so that spans about 5 months. So what we are seeing is, for example, like in November, we have a thermocline, we have a well-defined epilimnetic layer, metalimnetic layer, and probably apolimnion here. Then in December, we have the collapse to some extent of the temperature and with depth. So we have like pretty good concentration here, and then it decreases the way it decreased here. And then in January, we have the same, and then we have this oxycline here with oxygen, and then start February, March, we're starting to get this pattern, which indicates like we have like pretty high concentration in the epilimnion and then the thermocline, and then pretty much no concentration, I mean no values for oxygen below that, this thermocline. Metalimnetic oxygen minima. The opposite condition, a metalimnetic oxygen minima or a negative heterograde curve, is also commonly observed in many water bodies. Numerous physical and biological mechanisms have been attributed to causing metalimnetic oxygen minima. First, the basin morphometry of a water body can contribute to the formation of a metalimnetic oxygen minima. For lakes with a gradual basin slope and substantial contact with a metalimnetic layer, a larger area of the sediment will be in contact with metalimnetic water than hypolimnetic water. The oxygen reduction in the metalimnion due to high sediment microbial decomposition may be sufficient to extend laterally over the entire lake, or as in the case of scirculations, it may occur more strongly in the metalimnion close to the lake perimeter near the sediment metalimnion interface. Second, interflow from incoming stream can introduce low oxygen water or water with high sediment or nutrient loads in the middle of the water column, thereby resulting in greater decomposition in the metalimnion than the layers above and below. Third, a major biological driver of metalimnetic oxygen minima is the sinking and subsequent respiration of autochthonous organic matter in the water column. During stratified periods, sinking rates slow when the organic matter encounters denser metalimnetic water, allowing more time for decomposition. Moreover, decomposition rates are usually higher in the metalimnion, where temperatures are greater than in the apolimnion. It is also possible that a phytoplankton population responsible for forming a metalimnetic oxygen maximum could collapse, driving a subsequent metalimnetic oxygen minimum, as shown in figure 11-14. So I think what they're talking about is like we have like this collapse right here of oxygen concentration. Fourth, in certain situations, large population of zooplankton in the metalimnion can contribute to a severe reduction of oxygen. Such respiratory consumption was most likely a major cause of the metalimnetic minima observed in Zürichsee, Switzerland, and Lake Washington, where copepod can reach high populations. The reservoirs are prone to exhibit metalimnetic oxygen minima due to their morphometry and the prevalence of interflow and outflow extraction, which favor water currents in the middle of the water column. Reservoir water moving horizontally over the sediment downstream can become depleted of oxygen as the reservoir channel transition from the riverine zone to the lacustrine zone. This layer of water can become a metalimnetic oxygen minimum if the water column is stratified as the basin deepens at the dam. If water is being extracted from metalimnetic depth, the minimum can be further intensified by currents that entrain with this low oxygen water from upstream into the deep basin. During storm or periods of high inflow, interflow can further accelerate oxygen consumption in a reservoir metalimnion. Falling Creek Reservoir is a eutrophic reservoir with a strong metalimnetic minimum in the summer stratified period. The reservoir's ice-off occurs in March, with well-mixed conditions until March, similar to Lake Erkin. Falling Creek Reservoir exhibited early oxygen depletion at its sediments, while spring circulation occurred throughout the rest of the water column. The reservoir exhibited cleaner grade dynamics until the onset of a metalimnetic oxygen minimum in May, which became more pronounced in June and persisted until turnover in October. The high oxygen in the epilimnion during May to mid-July was due to high phytoplankton production. This epilimnetic production has likely contributed to the metalimnetic oxygen minima throughout the rest of the summer. The oxygen minimum was also favored by mid-water column extraction and the gradual upstream slope that implies high exposure of the metalimnion to sediments. One of the major takeaways from the Falling Creek Reservoir data is the substantial variability in its oxygen profile over the year, driven by a combination of human management, variable inflow volumes, high productivity, and the reservoir morphometry. Falling Creek Reservoir exemplifies the dynamism in oxygen conditions that many eutrophic reservoirs exhibit. And that's going to be it for today, and tomorrow we'll pick it up with oxygen dynamics in lakes with different mixing regime. So thanks for attending today's limnological session on oxygen distribution in lakes, and I'll see you tomorrow. Bye.